Section 19.3, electric power. The two objectives here are going to be to relate how energy is converted and the rate at which it's converted to power, and to calculate power about usual appliances around the house and its cost over a given time period. So first, in order to think about how a charge carrier moves through a circuit and potential energy, and we'll relate this to power, we have to think about a very simple circuit. And what's happening here is this. A charge in general wants to move from a higher electric potential to a lower potential energy. Just like we see when things fall from the sky, the object wants to fall to a lower gravitational potential energy line. Now, in a battery, the way it works is at terminal A, the charge carrier has a lot of potential energy. It's about to leave the battery, and it doesn't matter what direction we actually go in, right? So it wants to leave the battery. So it's got a lot of potential energy, and this is the charge carrier itself. And it's moving along the path, no energy is being used up, it's just moving from the electromagnetic field that's being induced in the circuit. And it's pushing until it gets here. Now it hits point B, and from point B to C, that energy is being used up or converted into internal energy. And that's what happens to cause the filament to warm up and to give off light. Now, once that charge carrier does its job, it's got no potential energy left here at this point. Okay, and it returns to point D. And it returns to point D as a result of being pushed through the circuit by the electromagnetic field. And when it gets back to point D, it's got no potential energy here. Well, it hits the battery, and the battery does work on the actual charge carrier. And the work done on that charge carrier brings it back to a higher potential energy, and it leaves at part A again. So we'll see the same diagram here. A lot of potential energy. It leaves the battery, it's traveling, hits the light bulb right here, and then from its duration across the light bulb, or across whatever the resistor element is, from B to C, it loses all of its energy. It's all converted here to light. Then it moves from C all the way back to D with no energy left, just being pushed along the way. And then once it gets back to point D, it needs to charge up in the battery or gain energy. So from D to A, it gains that same potential energy that it lost in the beginning. And then the cycle continues. So electric power now is defined as the rate at which the charge carriers lose their electric potential energy. And if we think back, remember that power, mechanical power at least, was defined as the rate at which work is done, right? That's what we started with earlier in the year. Well, we then went on to say that we could just say it's the change in energy over time. Now, in electrical power, it's very similar. We'll just say electrical power equals the change in electric potential energy during a given time period. So again, a rate, the minute you see a rate, it's got to be over time. The rate at which it loses electric potential energy, so the change in electric potential energy over a given time period. Now with a little manipulation and some substitutions, what we end up getting for power, and this is power in terms like voltage and current and resistance, is that power is equal to the current times the voltage, And you could see a derivation that goes from one formula to the other. I'm not going to show it here, though. So we know that the current times the voltage gives us power, and this is one of our three formulas we're going to use, but there are two other formulas. And the way we can show those other two formulas, very simply, is by thinking about Ohm's law. Well, this is Ohm's law here, and that IR is equal to V, really, right? V equals IR. So we could replace this V simply with IR in its place. So the second equation that we could get is P equals I times IR. Well, I times I is I squared, so this just becomes P equals I squared R. And then finally, there's a third equation we can use, and we can get that by solving for I up here. If you solve for I equals V over R. Now, if I equals V over R, we can substitute that in right there for I. Well, if we do that, what we end up getting is going to be P equals, now this is going to be V over R times the V that was there. Again, we're substituting V over R right there. So you get V over R times V. That's this right here. Well, that becomes power equals V squared over R. So it turns out, and you'll see them in the three boxed equations, that we actually have three representations for power that we can use. So in summary, those three representations are given here. Power equals current times voltage. Power equals current squared times resistance. Power equals voltage squared over resistance. And all three of these, again, have units of watts in them. Power we're calculating. So a TV is connected across a 120 volt outlet. The TV dissipates 1150 watts of power in the form of EM radiation, hopefully light, and that we're seeing, the visible spectrum, and sound. Calculate the net resistance, the overall resistance of the TV. So we have some sort of a circuit, right? And the voltage across it is 120 volts. And we know that the power generated or used by the TV is 1150 watts. So we know the voltage and the power. We want to find the net resistance of the TV. Well, remember that the TV itself, right? This object has some power cord going into it right in the back. So there's a circuit flowing in the power cord, right? Goes into the TV, comes out the other end of the power cord back into the wall. And this power cord is plugged right into the wall right here. So we know that there's a flow, and each internal element in the TV has its own resistance, but we're going to try and find the overall, what's called equivalent resistance of the TV using these factors. Well, given these factors, we're solving for R. We'll use the third of the three formulas, P equals V squared over R, because right away we have P, V, and R. So if we can solve for R in these equations, we can just manipulate it by switching the location of power and resistance. So multiply by resistance on both sides and divide by power. We'll get that the resistance equals the square of the voltage over the power. And just simply plugging in the numbers from the statement above, we're going to end up with 120 volts squared over a power rating of 1150 watts. Well, this gives us a resistance of 12.5 ohms. So the overall resistance of the TV is 12.5 ohms. Now, each component may be different, and it's not one of those situations where the sum of the parts equals the whole. So it's not like there's 12 parts of the TV, each with around 1 ohm of resistance. And we'll see more of that in the next sections when we talk about resistance of elements in series and parallel. So next we're going to talk about electric power cost. And think about an electric company. They send you a bill. The charge is actually for the energy used. And this is a bit counterintuitive since people have a tendency to call them power companies, when in reality it's the amount of energy that you've used from them. And the unit of energy that power companies base their calculations on are kilowatt hours. Okay, kilowatt hours, written that way, where it's a multiplication symbol. Okay, and you'll see it on your energy bill like this. Okay, kilowatt hours. And this is the amount of energy delivered in 1 hour at a constant rate of a kilowatt. Or to think about, real terms, a 100-watt light bulb for about 10 hours. Okay, 100-watt light bulb for 10 hours is 1 kilowatt hour. And let's think about what a kilowatt hour really means in terms of energy. Okay, well, where do these units come from, kilowatt hour, as far as energy? Well, here's where it is. Think of this formula. Power equals change in electric energy over time. This is the one we started today's lesson with. If we solve for potential energy, we get power times time equals change in potential energy. Well, power is measured in watts, time is measured in seconds. Well, the units that the company uses kilowatts and hours instead of watts times seconds. So clearly we can see that if this is a measurement of energy, watts times second, this also must be an energy measurement. Now, with that said, let's figure out what is a kilowatt hour. So we start with a kilowatt hour as our unit, right? One of them. Put a 1 in front here. And we want to multiply it. Let's get this into joules, right? Convert this all into joules. So I could start by multiplying this by 1,000 watts per every kilowatt. That gets rid of the kilowatts as units. Then I'll multiply this hours. Okay, we'll think of this as 60 minutes per 1 hour. Getting rid of my hour units here. And then multiplying this by 60 seconds for every minute. Getting rid of the units here. Leaving behind units of watts times seconds. And let's see the reasoning behind what I just did. Okay, when I multiply all these numbers out, I'm going to end up getting 3.6 times 10 to the 6. And again, my units are watts times seconds. Right? Watts times seconds. Well, a watt times a second is actually defined as a joule. And the easy way we can remember that is because a watt is really joules per second. So if I have this number here, in joules per second times second, well, these second units just cancel, leaving behind joules as my units of energy. So 1 kilowatt hour is really around 3.6 million joules of energy, to give you a consideration of how small a unit of joules, units of joules are. Finally, let's take a look and say to ourselves, how would you calculate the cost? How would you calculate the cost? Well, the cost that would cost you at the end of a month would be the amount of energy used times the rate. Times the rate, which in essence really means the amount of kilowatt hours, right? The amount of kilowatt hours used in energy times the rate, which is the dollars per kilowatt hour. And you'll see this rate on your electric bill, and it'll say maybe like 17 cents per kilowatt hour. So it'd be like 0.17, or 15 cents, 0.15 per kilowatt hour. It's the rate at which energy costs you. And you'll notice right away that if you were to get an answer for these and multiply them, those units would drop off, leaving behind dollars, which are the units of cost, dollars. So let's take a look at an example now where we can see this. So example 2 reads, you accidentally leave home without turning off the lights in your bedroom. You remember that there's 3 bulbs running on the ceiling light fixture, and each of them have a power level of 100 watts. Now you return home 10 hours later. If your electrical energy costs 30 cents per kilowatt hour, so there's your rate, there's your rate, because it's per kilowatt hour, what does it cost you while you're out for the day? So again, we'll list our rate to start. Our rate is 30 cents per kilowatt hour. You know that each light bulb runs on 100 watts. So right away we can think about the fact that we have 3 of those. So we're using 300 watts of power whenever this light fixture is on. That's the amount of power we're using. And it's on for 10 hours. Well, from a moment ago, we already came up with the idea, if you have the power and you have the time, you really do have the amount of energy used. Remember that power equals the amount of energy over a time period. So moving up the time period up over here and getting rid of it down here, the amount of energy that we use in this problem, remembering that our equation in a minute is going to be cost equals energy times rate. The amount of energy is really the time period times the amount of power consumed over that time period. Well, we have 300 watts as our amount of power, and the time period is 10 hours. But our rate units are kilowatt hours, whereas this is watt times hours we're going to get. So we should really convert this into kilowatts. So when we go ahead and calculate the amount of energy used, it's the time period, 10 hours, right, times the amount of power. But the amount of power is 300 watts, that's 0.3 kilowatts. So it turns out in the end that the amount of energy used, 0.3 times 10 is just 3 kilowatt hours of energy. 3 kilowatt hours of energy. In that one day of leaving your light bulb on, that's how much energy you use. Let's see how much it costs you. 3 kilowatt hours times a rate of 30 cents for every kilowatt hour. Units canceling. And 3 times 30 cents is 90 cents. So just by being out for that portion of the day, it costs you almost 90 cents. Now, to give you an idea of exact numbers, in like the city in Brooklyn, you pay like 20 cents per kilowatt hour. So maybe it'd be a little bit cheaper than this number. But just for leaving your light fixture on, that's one lamp on for one day, it costs you almost $1 for 10 hours. And that's the approximate time you'd be out of the house for the day when going to work or school.